All right. Welcome. I'm not sure why my camera is not. Where the hell's my camera actually? Okay. Um. Uh. All right. There we go. All right. Cool. Let's start this thing now. I'm also listening to blues, so I will be a bit weird today. Come on, camera not move it. All right, let's do this. Okay, so first of all, I don't know if I will be um doing a oh shit. If I'll be running some things on here. Um because I am unsure. I have to run this thing later. Uh I'll basically finish this whole thing first. So here, if I were to uh apparently, oh okay, so I can just install brew. All right. And while that's running its thing, let me enter my password. All right, another one. Uh, okay. I'll quickly do this one. I'll probably not finish the whole thing. So first, we'll go to workspace, Dinosaurs, and then we will. Okay, so when a program the CPU translates. Here you go. When a program accesses memory, the CPU translates a specified address, virtual address, into a physical address. The table that maps virtual addresses to physical addresses is called a page table. By switching page tables, the same virtual address can point to different physical addresses. This allows isolation of memory spaces. There you go. So that's when you isolate for and separation of current application memory areas, enhancing system security. Hardware-based memory isolation mechanisms. So in this book, we'll use specify a paging mechanism called SV32, which uses a two-level page table. 32-bit virtual address is divided to first level page table index, which is this one, and second level index, which is this one, and a page offset. Try to see how. Oh, oh, it's fine. Okay, so, right. So that's how it works. Changing the middle bits doesn't affect the first level index. Doesn't mean that tables. The principle allowing for smaller page table sizes. Okay. Um. Okay. So CPU calculates VPN, virtual page. Is that what the VPN stands for? Identify corresponding page entry. Okay. So kernel.header. Let's make some micro. Oh shit. Let's What was that? Let's write some macros. So, oh shit, how do I? Ah, so, um, we're going to write down here, or maybe a bit up there. Maybe somewhere. So, we'll define. Well, so we're gonna construct a page table. Okay, this is a page table. What we're gonna do is define 7 macros. I think. Wait, 7, 6 macros. So, SATP SV32 IU31. Then we'll define page V, which is I0, page R. So this is apparently a valid bit, and that entry. Okay, constructed in SV32, and we know that SV32 is RISC-V's paging mechanism, which is a 2-level page table. And I'm gonna write some more. 32-bit virtual address divided into first level. You know what? Let me. There we go. 32-bit virtual address is divided into first level, and then second level, and then page offset. First level page index, which in this case is a VPN, VPN1. This is also a page. This is also an index, which is VPN2, and page offset. Changing the middle bits, which is this one, first doesn't affect first level index. This means page tables, entries or nearby address are concentrated at first level. Changing lower bits does not affect either. This means address is paid. Principle of locality. Check principle of locality. Smaller page table and yeah, honestly, I still struggling to understand this part, but I'll continue as it is now. Basically, CPU access memory. It'll calculate the first level page index. Okay, and oh, sorry. And then the second level page index, right? To get corresponding page table entry. All right. Then adds. That's how it works essentially. So that's how you do your page table. Next is oh yeah, SATP over here is single bit in the SATP register, which basically enable paging in SV32 mode. And these macros flags to set in page table. So this one would be readable. This one is readable. Readable. This one is 1, 2. Writable. This one is 1, 3. Executable. Page U. This is the user, which is accessible in user. All right, let me go check on something. I'll be right back. Right. I went to lock the gate. I'm back, and we'll continue. Oh shit! Hello. GitHub. Sure thing. Yeah, no problem. Anyway, just send it over, and I'll check it. Can't believe there's actually people watching this. It's very interesting. Right, so let's do some mapping pages. The following takes first level page table, the virtual address and the physical address. Uh, hmm. Oh my gosh. First level page table, virtual address and physical address, page table entry flags. Okay, the function ensures the first level page table entry exists, creating the second level when needed, then sets the second level page table entry to map the physical page. Divides the physical address by page size because the entry should contain the physical page number, not the physical address itself. Mm. Uh, what's this? Okay. So, what this is doing is this is so the map page function, okay, takes first level page table, the virtual address, physical address. So we are essentially mapping the page. Uh, mm, uh, First level page entry exists, then sets the second level page table. I sent. Give me a second, y'all. Uh, okay. Mm, mm. No problem. I'll check it. Quick checking. Yeah. Nice. That's pretty cool. Yeah, this is pretty good, man. Good job. Mine is, mine is just eh. So don't expect anything from me. But this is good. All right, good job already. All right. That's good. That's good. That's good. This is I think it's yeah. Okay. Yeah. Good job. Okay. Um. No problem. Right. So let's continue our thing here. I'll give you a follow. Actually, I like to follow people. I'll have to. That would be cool. But I'm pretty busy, so I'm not really sure if I can. So, it'll be great though. Then you know. Right. So, function ensures the first level page table currently exists. Creating table second level needed. Then it sets the second level page table. Right. So what we are doing essentially is uh memory mapping page. Mm, all right. Yeah, so yeah, we're what we're basically doing is this shit. Oh, I'm 18. My age. I'm 18. Just turned 18 like last year. Okay, so page table. Yeah. So this is essentially what we're doing. And we're gonna map the pages. We're gonna map the pages onto the physical memory. All right. Yeah, there you go. A page table maps virtual pages to physical frames. Uh, so you see here, virtual pages. This is the virtual here. It maps to physical frames because it's different. Physical memory has frames. Virtual has pages. I think that's how it works. Hopefully. By the way, I'm not claiming to be an expert in this at all. I am a complete idiot trying to understand this. All right. So don't trust me on the things I say. Um this stream was not meant to be seen by anyone. It's supposed to document my bullshit, but I thought, fine, I'll post it. Maybe in the future I'll come back and look at it. Right. Let's write some functions. So I'll probably write a little kernel entry here, right? Um, no. Actually, I might put it around here. So this will be mapping pages. Right, we're gonna be mapping virtual pages onto physical memory frames. All right. So we're gonna make a new function void. Okay, so basically it will return basically nothing. Page, right? And it will take an unsigned integer uh table one. Define. Let me just explain here. Table one is the first level page table. V address is the virtual address. PADDR is the physical address. And flags are page table entry flags. Okay. And here, uninteger 32. Okay, unsigned integer, as usual. We'll take the virtual address. We'll also take the physical address. And then we'll also take the, oh yes, the flags, correct. That should be it. Yes, so. Alright, let's do some if statements. So if the, oh yeah, we wrote this function, didn't we? So if, alright, the virtual address and the page size is not aligned, then panic, we're gonna make a kernel panic, we're gonna throw a kernel panic, unaligned virtual address. Boom. Alright, and then virtual address, there you go. Alright, easy, right? So, and then if the physical address is not aligned with the page size, then we panic as usual. Unaligned physical address. And then print the physical address itself. Right. Also, bro, I'm also learning OS concepts by books. I mean the Linux programming. Oh, nice. Here is the website that I'm on. Oh, oops, sorry. This one. Nice. It's great that you. Oh yeah, you use Arch as well. I mean, not as well. I don't use Arch, but hey, good job. Really nice way of learning things, actually. Undeclared. What do you mean undeclared? Oh, Use only client identifier. I'll fix that later. Hello, who's this? Hi, nice to meet you. I'm not sure why that. Hello, welcome. Anyway, so next we do unassigned integer 32, right? VPN1, which is the okay. Okay, is equals to the virtual address 22 and 03 FF X03. Actually, sorry, and actually, what? I have never used this before. Oh, hello, Mr. Pello. How are you? Um, how long have you been coding? I've been coding since I was 12, so you could say 6 years already. I've been coding since 12 years old, and honestly, I don't know why I'm still doing this. uh, okay. Oh, so it's bitwise operations. Oh, it's a right shift. Right shift. So it requires two operands. It shifts each bit in its left operand, so it shifts the address to the right. And the number following the operator decides the number of place the bits are shifted. So we are shifting virtual address by 22 places. Crazy, man. I mean, I started. Oh, no, good job. Good job. Oh, did someone send me a message? Not sure. Someone's sending me messages. Oh, never mind. Someone sent me a spam message. So, all right. Next, okay. So what we do next, right? And you're it's a bitwise and, okay, here. So you're gonna get 0, you're gonna get 0, 0, 1 here. It's just an and operation, okay? Basically, if false and false, that's false. False and true, no. False and true, still false. True and false, that's false. Only if true and true, then if true and true, then it will be true. All right, that's the bitwise. I'm sure a lot of you have the. I don't even know what's going on. No. That's all right. That's all right. That's all right. I'm coding an operate. I'm sorry, writing an operating system in C, and you don't have to understand anything about it. I don't understand a lot of it either. And if you watch this stream, then you will not understand it either. All right. Okay. So we will start. All right. Table 1. Um. And with page. So if table 1 and page V, which is page V is in the header file here, if the valid bit, all right, if this is valid bit, and this is the hold on, VPN. So VPN1 is the oh my god. VPN1 is the first level page index. If the first level page index, okay, and the valid bit is 0, that means that there is no page table. Okay, so this means Okay, there is no page table yet. No, there's no first level page table yet. All right. Have you tried code for? I've never heard of that actually. And also C++. I have not tried C++. I will eventually. One day. One day. Okay, so since there is no first level page table, we're gonna create one. Right here. So what we do is so an unsigned integer. Okay, we'll make a new variable called point pt physical address is equals to allocate pages. What function is that? I've never seen that function before, haven't I? Pages. What was that function? Oh, did we already wrote that function? Or is my memory just foggy? Did we write that? I'm not sure if we wrote that. Did we actually wrote? Or is it or am I just confused? I think I'm just confused. Yeah, I may be just confused. Okay. Table 1 is equals to the pt address divided by the page size. So here we allocate one page. Oh yeah, we did write this, sorry. In memory allocation. We allocate one page of memory. Okay. And we divide it with the page size. And then we shift that by 10, allegedly. And then, or page B. After that, set second level page entry to map the physical page. Here, we do another, we define our second level, and then do the same thing. Not sure why it has to be 3. I'll explain later probably. And then table 0. Sorry. Table 0 is equals to the so we're gonna cast this into a pointer, which is table 1 vpn1. Where did the music go? Hold on. All right. 10 times page size, and then table 0. I'll have to go read on this later for more information because I don't think I understand everything. Physical address divided by the page size, 10, and flags page V. Right. So I will add a to-do here. Read more on RISC-V memory allocation. Paging mechanism. It's V32. All right, this function ensures the first level. Oh yeah, that's true. Shut down because it's all right. It's all right because yeah, it boosts pretty fast. Yeah. Okay, physical address and physical page numbers. Okay, so this function ensures first level page entry. exists, creating the second if needed, sets the second level page entry to map to the physical page. All right. And then it divides, so it divides the physical address here. I think it's referring to here and here as well by page size, because the entry should contain the physical page number, not the physical address itself. I'll quote it here. All right. All right. Hopefully, oh, there's not that much and not much stuff left actually. So, kernel.c is done. Then we're going to manual. So the page table must be configured not only for applications but also for the kernel. That's correct. This build the kernel memory mapping is configured that the kernel's virtual addresses must match the physical address. So basically, the virtual address is equal to the physical address. This allows the same code to run even after enable paging. First, let's modify the kernel's linker script to define the starting address used by the kernel. So, kernel.linker. So, here we will start here. So define a section, right? Kernel base is equals to dot. Define kernel base. If the order is reversed, the valid kernel will be 0. Ah, yes, because the dot means the current my typing speed around 100 words per minute. I think. I'm not sure. Sometimes around that 90 to 100 words per minute. It's probably higher than that. Who knows? Next, the page table to process struct. Add the page table to process struct. This will be a pointer to the first page. Okay. All right. Back to kernel header. Oh, sorry. I think this one's already done. Oh, that's good. Oh, brew install LLD. I thought LLD is already installed, isn't it? Ah, okay, good. Okay, so let's go to the process over here. So we will add a section here, which is unsigned integer page table. This is the pointer to the first level page table. Actually, I should commit some of this first. Give a quick check. Yeah, I'll check on when after I hold on. Let me hide this first. All right, let me push some things to my push some changes first. So started working on paging, constructed page table and mapping the pages. Then git push. Oh, okay. Cool. Actually, let's try. Let's rest a bit after. No, not really rest. I'm gonna do something as the chat has requested, which is I'm gonna check my typing speed. So, right here, I have no idea. I haven't checked it in a while. So let's try. Oh shit. Oh, what's that? Please get to that. Oh. Oh wow. 108. Not bad. The raw speed is 112. Nice number. That's not bad. There you go. Oh shit. I forgot to reshare my screen, didn't I? Oh, I already shared. That's just crazy. Well, I've been doing this for 6 years, so it's normal, I guess. Right, I'll finish this and we will uh give on that. That's for the birds. All right. Let's try. Words 10. Okay, so shit. What the hell? What the hell? Let's try again. Hold on. That was weird. Ah, 98. Oh, that's weird. Oh, but the raw is 118 though. Because this also accounts for accuracy. So the raw speed is 118. Oh well. Anyway, let's continue. Let's go to kernel.c. And we will lastly map the kernel pages to the current create process function. The kernel pages span from kernel base to free RAM end. Yeah, that's correct. This approach ensures that the kernel always accesses both statically allocated areas like text and dynamically allocated areas manned by allocated pages. All right, let's go down to if I can find it. That is, there it is. So extern. Wait, no. Oh, extern character kernel base. All right. So this is a kernel pages span from kernel base to free RAM end, and make sure kernel always can access static allocated and dynamic allocated. Simple. Okay, so we will do some checking here. All right, we'll add a add page table, which is basically mapping the kernel pages itself. Because we must remember, right, the kernel. Yeah, I'm not flexing. God damn, 128. That's good. Good job. Try code C on monkey type. I don't think I can. I don't think you can set it to do that, right? I'm getting distracted, but that's all right. Can you? Nah, I don't think you can. It's fine. I'm not a change. Oh, you can. Let's try that actually. Int main. Let me. So this is gonna be like the input, right? And I'm gonna like code like hello world. You can apparently, and it will turn 0 because we are not returning anything. Right? All right. Hello world in C. Oh, I can't save. Oh, because I have to be signed in for it. Whatever. Yeah, it's all right. I'll set later. Next time. Okay. So I'm signed in 032. Let's find a page table, and then we'll cast here. Right. So we're allocating a page of memory. Right. Because we must remember the virtual memory is divided into different pages, right? For those who are new to this, right? We're basically dividing it into pages, essentially. Yeah, see? Here. These things are called pages. The physical memory shit, these things are called frames, right? And we're mapping the page to the frames. In this case, it's a direct map. As in, if the virtual memory address is A, then the physical memory address would also be A, right? Because this is a very simple. You missed the okay. Oh, really? Really? Oh, I'm stupid. Really? All right. Oh. Oh, you don't have to save. All right, let's try. All right, let's try it again. Let's try it again. Let's try it again. Let's try it again. All right. I don't think I can reach 100 with this. All right. What the hell? Seriously? Can you set time? Oh no, you have to be custom. All right. So, oh my god. Oh, what the hell? Oh, this is so weird. What? Oh, that's, oh my gosh. Return 0. Boom. That is so stupid. Oh, what the? Well, I started from like 120 and then it just went down to 44. Cause like I'm not good try. Proper settle and you can change it. Oh, okay. Interesting. Interesting. Alright. I accept my defeat. 44 words per minute. But yeah, it's alright. Let's finish this because I will have to go to sleep soon. So, um, sorry, allocate pages, right? And then for loop, let's go for loop. So for physical address T, so this is a type, by the way. The T stands for type, and it's the macro, which is a shorthand because I'm too lazy to, C programmers are lazy to also write other shit as well. So, that's how they do it. So kernel base. There we go. So we cast, right, the kernel base part as a physical address so that we can assign it to the variable called PADDR, right? And what we do next is that P address is oh right, this is a for loop. All right, so P address is like I equals 0. This is P address equals to the P address kernel base, right? And then as long as the physical address PADDR is less than the free RAM, and because remember, we're allocating from kernel to free RAM end, and if you look at the stack memory, how stack memory works, right? Stack memory, okay, it begins from the bottom here, right here, right? And then when you start using it increases upwards like that. Whoa, wait, does it lower like that? Nah, 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 nah. Sorry. No, that was a bit. Wait, no, hold on. Oh, right. Um, That is so weird. Which one am I supposed to trust? This doesn't look... This looks really weird. Oh gosh. In the main screen. Sorry. Oh, okay. I'm so confused. Hold on. Wait. The stack increases from the bottom, right? Wait, the origin is up there, but when you go 0 to 28, you go up, correct? What? Oh. So, okay. The high memory address, right? And you would be, no, hold on, kernel. Oh, wait, no, this is like the entire, you're going through kernel base, which is that memory area, and then you go towards the end of the free RAM section. And I think that's the heap, isn't it? No, that's the entire memory. If I remember right. Most Gmail scene coding. Oh, come on, don't say that. Don't say that. I'm extremely average. All right. This is like very basic. Like this is like tired as 18-year-old coding a operating system, right? I admit, fully admit that I do not know this that much. This is the purpose of this is to educate myself. And if it educates you as well, then I'm very happy. All right. So yeah, so if okay, so the high address, because if you go back to, you know what, let me open on if you look at the linker, right? The kernel base, um yeah, kernel base is at that memory address. That is the kernel base memory address. Then, if I remember correctly, what we'll be doing, so it covers the entire thing from that memory address to the end of the free RAM region. Okay. So it goes from that address, it goes to the end of the free RAM section, which is essentially the entire memory, right? So what we're doing here is, as long as the physical address is less than the physical address of the end of the free RAM section, okay, then increase increase the physical address by increment the physical address by each page size, okay, which is in this case, if I remember correctly, 4096 or 4 kilobytes, I think. All right, see ya, man. Thank you so much for watching. I'll see you later. Have a nice sleep. Good night. See you next week. All right. So then what we do next is we will here. Okay. I think it's better if I put thing there. And then we will map page. Alright. The page table. Correct. The physical address. The physical address page R, page W, writable, and then executable. Is that correct? X stands for executable. Yes. So we're basically saying, I and All right. Then we add a semicolon there. Now these errors down here is a bunch of warnings, and I don't really give a damn. Okay, so this one you already wrote. So basically, look for. Okay, so we're from kernel base to free RAM end allocate page tables. No, increment physical address by page size. Essentially, mapping kernel page. Easy. Then process page table. Oh, I didn't mean to add a comment like that. Page, because we are assigned it to the struct as we define a struct, and then page table. All right. I thought there we go. Yep. All right. Then we will go to the yield function, volatile here. I think so. And we'll add a bunch of lines here, which is sfns vma. And we'll write sfns vma ensure changes to page table are properly completed, and also clear cache of page table entries, which is the TLB. And then CSRW. So control state register, right? Value, I think the value of SATP. Right. Then I can just copy this line, can I? Yeah. Oops. All right. Something like that. SATP. Unknown. What do you mean unknown? You know this. Right. And then. Oh, this is a trailing comma, isn't it? Okay, so. This is SATP R TP SV32 and unsigned integer 32T. Next, page table. All right, divided by page size. There we go. We can switch page tables by specifying the first level page table in SATP. Note that we can divide page size because it's the physical page number. Here, we can switch. Okay. So there are switching page tables. Pause. Context switching. Okay. Here. Yep. All right. Be everything. Cool. And hello, welcome. Okay, so that should be it, isn't it? And then what we can do is we can run the thing. Oh, oh boy, what is this? Uh, what the hell? Unused parameter. Yeah, that's fine. That's just morning. Call to undeclared function. Huh. Did I forget something? Kernel.c 114. Oh, yes. I think I wrote it wrong. Sorry. Yes, this is a bit incorrect. Undeclared. Kernel.c. No, common.h. Sorry. I'm so confused. Did I write something wrong? Oh! I didn't write that properly, did I? Build in. Did I? Um, Call to undeclared function. What? Expanded from the macro. Oh. Oops. Yeah, okay. Now we just have a problem with risk 5. So now I have to build the thing, which I'm not sure. Um, oh yes. Okay. There we go. Uh, interesting. 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 Uh, all right. Google time. Pretty sure this is Clang. No, sorry. Okay. What is this? 4 years ago. You know what? I'll test this later, actually. I'm a bit too tired to uh hmm uh okay. Yeah, see? Pre-installed Clang. Uh oh. Install another Clang. Uh, opt user local opt LVM slash uh bin Clang. Help. Hello, welcome. Welcome. I'm diagnosing Clang right now. Uh, oh, there it is. So, I basically have to switch the. You know what? Fine, fine. Uh, run sh Clang. All right, here. For Linux, use this. For Mac, my Mac OS, my iMac, use this. All right, cool. Yes, of course, of course, of course. Hi, welcome, welcome, welcome. Shit, what have I done? All right. In theory, it must run. The output is exactly the same as the previous chapter. There's no visible change in the image. Ooh, interesting. Did I not do the what the hell? I thought I'm from Thailand. Yes, Thailand. Thought I pulled everything, didn't I? Did I not do this properly? What did I do? Yeah, that's perfectly. Ah, okay. Yeah, then there's no problem. There's no problem because it runs perfectly. See? Starting process. Switch back to idle process. See, it works perfectly. There's no visible changes after enabling it. To check if we set up page tables correctly. Ah, nice to meet you. Hello. Let's look at how virtual addresses are mapped. Okay. If set up correctly, right, we will do this. They should be mapped. Virtual address should be equal to the physical address, all right? Oops. Control AC. Stop. Okay, info registers. Okay. If we check here, where's SATP? SATP is this one, yeah? 8008231. Not sure why it's that. Through 3. According to interpreting this value gives us the first level page table starting physical address. Yeah, and times 4. Yep. Next is by the contents of first page level. Okay. First entry is 4 bytes. Hmm. Physical page number. This is so weird. Alright. I am not sure how I am supposed to debug this and confirm that this is, I mean, it works properly, right? It runs okay. So let's just say it works. Alright, so git add everything, git commit m, added, finalize. Done. If you check here, yep, done. Awesome. All right. So, well, that should be the end of our stream for tonight. Thank you so much, everyone, for tuning in. I'm very happy that there's actually people who watch with me. But at the same time, it's not my purpose of doing this. So, thank you nonetheless. All right. I'll see you later. Bye bye.